velocity of sound in an ideal gas. When a pressure disturbance occurs in a compressible flow, the disturbance travels with a velocity that depends on the state of the fluid. When a pressure disturbance occurs, in a compressible fluid, the disturbance travels with a velocity that depends on the state of the fluid. A sound wave is a very small pressure disturbance. Wave is a very small pressure disturbance. The velocity of sound, also called the sonic velocity. Is an important parameter in compressible fluid flow. We proceed now to determine an expression for the sonic velocity of an ideal gas in terms of properties of the gas. Let a disturbance be set up by the movement of the piston at the end of the tube. This picture shows the Chapter17, a wave travels down the tube with the velocity c, which is the sonic velocity. Assume that after the wave has passed, the properties of gas have changed in an infinitesimal amount, and that the gas is moving with the velocity dv through the wave, as also shown here, travel with the velocity v. In the figure B, this process is shown from the point of view of an observer who travels with the wave from control surface is changed and is on the wave. Consider the control surface in this picture. From the first law for this steady state process, we can write for B H plus C speed of or we can write dH from the continuity equation. We can write rho AC dH equals to excuse me consider also the relation between properties. If the process is isentropic, ES 0, and this equation can be combined with the equation here, we can conclude that dP on rho dV 0 dP on d rho. Since we have assumed the process as entropy, we can write at S constant. An alternate derivation is to introduce the momentum equation for the control values shown in the B figure B. The momentum equations can be written as this expression. It will be of particular advantage to solve the equation velocity of sound in ideal gas. When an ideal gas undergoes an isentropic change of state, we found in Chapter 8 that for this process, assuming constant specific heat, dP on rho or rho P on Substituting this equation, we have an equation for the velocity of sound in an ideal gas. We can write c square on rho or Cp on rho RT for the gas. KRT Cp on Cv, and R is a universal constant. Reversible adiabatic one-dimensional flow of an ideal gas through a nozzle is the next section.